Okay, good afternoon. In today's session, I'll be discussing some numerical examples on simple stresses and strains. Basics already have discussed. So here, the first example is on composite bar subjected to tensile force. Okay. What it reads is the bar shown in figure is subjected to a tensile force of 160 kilonewtons. If the stress in the middle portion is limited to 150 Newton per mm square, determine the diameter of middle portion, also the length of middle portion, if the total elongation is limited to 0.2 millimeters. So stress we need to find, diameter we need to find. Okay, so we call it D2, and diameter of end portion is given, and let length of end portion combined is L1 by 2, that is L1, and length of middle portion is L2, diameter is D2. So how to find D2 satisfying the condition the stress is 150 Newton per mm square, and we have to find length L2 satisfying the condition the total elongation is 0.2 millimeters, and Young's modulus is given 2.1 into 10 power 5 Newton per mm square. Okay, so the total length is given here. L1 plus L2 is 40 centimeters or 400 millimeters. Okay, so we can find area because we know the force here and stress. Okay, because the stress is given as force by area. The force is 160 kilonewtons and stress is 150 Newton per mm square. So we can find area and from that diameter. Okay, so area of this is pi d2 square by 4. Okay, so d2 diameter of middle portion and L2 length of middle portion. So here what we have to use, the formula is stress sigma equal to P by A. So P is 160 kilonewtons into 10 cubes newtons by pi by 4 into d2 square, and which is equal to sigma, that is equal to 150 Newton per mm square. 150 Newton per mm square. So from this you will get pi by 4 d2 square equal to 160 into 1000 by 150. Our d2 from this is obtained as 36.85 millimeters. The diameter is 36.85 millimeters. Okay. Okay, this is diameter, and length we have to find out. So length of both end portions combined is L1. Okay, that is L minus L2. L1 is L minus L2, that is 400 is total length minus length of middle portion, that is equal to L1. Okay, now the total elongation is given, which is 0.2 millimeters, and that is equal to P. P is 160 into 1000 by E 2.1 into 10 power 5 into L1. L1 is 400 minus L2 by A1, that is pi by 4 the diameter is 60 mm. Okay, yeah, diameter is 60 mm, 60 square plus L2 by A2. L2 by A2, that is pi by 4 into diameter of middle portion we have calculated 36.85, 36.85 square. Okay, so this is equal to total elongation, which is limited to 0.2 millimeters. Okay, so solving this, we will get L2. Okay, by solving this, we will get L2. Okay, yeah, it is coming out to be 207.14 millimeters total. That is the length of middle portion, and diameter of middle portion 36.85 millimeters. So these are the length and diameter satisfying the given conditions of stress and elongation. Okay, now let's see second example. So here in the previous cases we have seen constant force acting, that means the stress being constant throughout. But here, by seeing the figure, it is clear that the forces are applied at different sections A, B, C and D along the length of the member. That means the portion AB is subjected to some load, BC is subjected to some other load, CD also is subjected to some other load. Okay, that means different portions will have different stresses and also different elongations. Okay, so what you have to find out is a brass bar having cross-sectional area 1000 mm square is subjected to forces as shown in the figure. Find the total elongation of the bar. Total elongation delta we need to find out. E is given, Young's modulus 2.05 into 10 power 5 Newton per mm square. Now if you observe this, at A we have a tensile force of 50, at B we have a force of 80 actually acting rightwards. Okay, for portion AB, if you consider the equilibrium of these sections, if you cut this here, for equilibrium we should have a force of 50 at section B, a force of 50 at section B. Okay, because total force of 80 is acting here at B, but out of which only 50 kilonewtons is taken by portion AB. How about the remaining 30? Here we will have 30 and you consider B, C, D now. Okay, yeah, 50 plus 30, total is 80. Total force at section B is 80. 50 on AB and 30 on BC or BD, you can say. Okay, remaining portion. And how about the force at section C? It is 20. And force at section D is 10. Now we consider again the equilibrium of section BC. If you consider BC, we have 20 here at C, compressive, and here we have 30, but out of which only 20 will be taken by BC, and remaining 10, which is acting at B, is taken by BD, because BD is subjected to tensile at D. So you will have you will have 10 kilonewtons at, it is not tensile here, it is compressive actually. It should be compressive because total leftward force is 80 and rightward force should be 80. 50, 20 and 10. This should be compressive actually. We need to correct. Okay. So on BD, if you consider, you will have compressive force of, let us consider that separately, BD. Here 20 is there, remaining 10 will be acting on BD. So this is compressive here, 10 and 10. So this is acting leftwards. This is not correct. So this force should be acting leftwards. Okay, 10 kilonewton. What does this mean? AB is subjected to tension, that means elongation. BC and BD are subjected to compression. Okay, so the total elongation is elongation of portion AB, compression of portion BC and compression of portion BD. So the total is obtained by adding these three changes in length. Okay, so let us see now, as we have seen, AB is subjected to 50 kilonewtons tension, BC subjected to 20 compression and BD to 10 kilonewtons compression. Lengths are known. The lengths are 600 mm, 1 meter and 1.2 meter. Okay. So area is known, Young's modulus is given. So we can find elongation delta L1 here, DL1. No? So it is DL1 is PL1 by EA1. PL1 by EA1. Here area is same for all. Area is same for all. So P is 50 kilonewtons and length is 600 mm by Young's modulus 2.05 into 10 power 5. Area is 1000. So you will get this equal to 0.2857. This is increase in length. That is positive side, increase in length. And DL2 is PL2 by EA2. PL2 by EA2. That means P is here in this case, you can say P1 and P2, you can say. P2 is 20 kilonewtons. This is compressive, so you will have decrease in length. And L2 is 1000. E is same, material is same. So A is same, constant. So this gives actually 0.1904. 1904. This is decrease in length. So while adding, you have to take negative sign here for this and positive sign for this. And DL3 is P3L3 by EA3. So P3 is 10 kilonewtons, L3 is 1200 divided by E into A. So this comes out to be 0.2095. This is also decrease because compressive. So it is also with a negative sign. So while adding, we have to take this positive and these two negative. So the net change in length DL is minus 0.1142. So there is net decrease in length by 0.1142 millimeters. 0.1142 millimeters. Okay. So the length of BC and BD decreases and that of AB increases. So the net deflection, net change in length of bar AD is negative, minus 0.1142. Okay, yeah, that's how we'll find out. Now consider third example here. Actually, this is a derivation. Elongation of bar due to its own weight. So, if a bar of length L and cross-sectional area A is hanging from a support, as shown here, due to its own weight, in case of heavy bars, it will have considerable length and there will be slight increase in length due to its own weight. Okay, how to find that increase in length here, change in length due to own weight? For that, you consider the bar of length L, cross-sectional area A and Young's modulus E, and unit weight of material. When you consider self-weight, unit weight comes into picture, because weight is equal, total weight equal to unit weight into volume, isn't it? Weight into volume gives, unit weight into volume gives total weight of the bar. Okay, so now for finding out this, we consider a small element of length dx at a distance x from the bottom end B. Okay, it means on this element the weight of portion, hatched portion, so you call this x, section x, the portion below this section will be causing the elongation of this elemental strip. Okay, because at this section you will have a force, downward force due to downward force P, which is the weight of this hatched portion. Okay, understand? So this will be acting here at this section, which causes the elongation of this elemental strip. So what is the length of elemental strip? Dx. Okay, so the stress acting here, the stress weight is unit weight into volume. Actually, unit weight into volume. Unit weight is W and volume is A into cross-sectional area A into length x. Okay, now the stress at section x is P by A. P is W AX divided by A, that is WX. And strain vachesi sigma, stress by Young's modulus, that is Wx by E. Stress is Wx divided by Young's modulus. And elongation of the element means the strip of length dx. Okay, strain into length, strain is Wx by E into length of element is dx. Okay, is it? So this is the, actually this is not delta, the elementary dl you call it, or elongation of strip. This is the elongation of strip. How will you get the total elongation? Total elongation of the bar is obtained by integrating this, okay, between the limits 0 to L, 0 to L. Okay, integration of Wx by E between the limits 0 to L dx. Okay, so you will get W by E. W is here unit weight. Integral x, that is x square by 2 between the limits 0 to L. So you will get WL square by 2E. And you can replace WL by capital W, the total weight of bar. Capital W is total weight of bar. So the total elongation of the bar is WL by 2E. WL by 2E. Okay? Yeah. These are all simple examples. Okay? We'll see some more example in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.